Is it recording? Yep, it's recording. Hey guys, so I posted this video on August 20th, 2016, and yeah, there's only 11 views, there's one like, and this guy right here, uh, I don't even know how to pronounce that name, but you have to share schematic and code design, smiley face. Well, I am a sucker for smiley faces, and I'm a sucker for sharing. Now, first of all, a little disclaimer. If you're planning on selling this for commercial use or you want to steal my idea, fuck you. No, none of that. Okay, I make these projects for the pure enjoyment of sharing them with the world. I don't do this for profit other than, like, I run ads on my videos because I need to make money too, or my job isn't the best. But if anyone shows interest, I am more than happy to help. Growing up, I wanted nothing but help, and do all my own research. But yeah, so I actually made all this stuff in preparation for this video. I did everything just randomly, as most of my projects are. I don't plan a lot of them. Well, this project I did not plan. I literally, one day I had a block of wood, I cut it with my saw, and then it was my girlfriend's birthday, and boom, pot. So this is a 3x3 inch pot, and this is a almost exact replica of the one in the video. This one. So I drew it in SketchUp, and if you guys want the SketchUp files, they're not super accurate to the actual thing, but I mean they're pretty close in terms of all the hole placement, the size of this hole, the way that this is incurved. The bottom is the only thing that's not super accurate to how I did it, but then again, I did it all with chisels. I have no CNC machine. I didn't have any special tools to make this. I just used what I had: drill and chisels and a hammer and a vice grip. I mean, not a vice grip, a drip thingy. So this doesn't tell you much about the actual circuit, but this does. But we won't go into that yet. So the way that I designed the pot would be easier if we can actually see the inside. So you can see here it goes down. So this is 3x3 inches, and then this hole in the middle is 2x2 inches by 2.5, or by 2.25, I believe. I totally forget. It's in real, yeah, 2 1/4 inch. In real life, it's not this clean and this accurate, but it's pretty similar. So basically, it goes straight down for about 2 inches, and then it goes out, or it goes inwards for about a fourth of an inch, or I don't think it's a fourth. Yeah, 1/8 of an inch on all sides. It goes inwards to create kind of a negative area for dirt to accumulate in here. So if the pot accidentally tips over or whatever, your plant won't just fall out. It'll have a little bit of grip. And for the actual sensors, so here are the two soil probes. You need two probes, obviously, for soil, so that's what these metal rods are. Now the holes I drilled into the wood to go into the bottom chamber are actually just a bit smaller than the actual metal. So when I pressed the metal through it, it would make a really nice tight seal. But I'm also hoping that the silicon, like I said in the video, the silicon would also act as a water barrier. Now this little black thing, I don't have a model for an NTC thermistor, but that's what that is. So to keep the wood from rotting, like I said in the other video, there is some silicon, and then it's coated with a fine layer of sand, just to add some more grip. Now the silicon is also coating the probes, and sand is also coating the probes, but as soon as the silicon dried off, I scraped off a little bit of the sand and silicon on each of the probes so that it would make decent contact. The water going through the silicon and through the sand is enough to actually make it in contact to be measured by the circuit. So yeah, that's totally fine. Now the bottom, So I used carbide drill bits, PCB drills, and a Dremel to drill out these holes, which are very small. They're smaller, I would say half of 1/16 of a drill bit, so 132 or even smaller than that. This model doesn't use the exact drill bit that I use because I couldn't make a hole small enough. The program just doesn't allow me. And then the LEDs are a bit recessed in. It's not recessed like this, and the holes that I made are not square. It's just I was having issues drawing circle holes. So basically it's the small hole right here and then another hole just big enough to fit the LED in, and then it's glue gunned in place. And it also has to be a bit recessed or else the light will pour into the other holes. So you have to put them inside, or if you can only put it in, say, like halfway, like 2 millimeters, then you can wrap the rest of the LED in shrink tube so that it blocks the light. And my phone is dying like a motherfucker. Okay, so let's put this back to face. So this in mine, I actually have this a little piece of wood right here that separates the battery and that. You don't have to do that, but you do need to chisel out this area also. And then as you get to the LEDs, you do need to make it go in a bit to fit the LEDs. Or if you use smaller 3mm RGB LEDs, I don't think those exist. Obviously, you don't have to use the through-hole ones either. You can use whatever RGB LED you have as long as it's a common anode. So these all have like red, green, and blue pins are all the negatives of the LED, and they're all common together through the positives. So that's what these are. Now, because it's 3 by 5, so that's 15 LEDs. There's only 13 ADC or 13 GPIOs, and I guess you could use the other ADC pins as pins to control each LED. Or I'm sorry, it's 3 by 5 is 15. But why would I do that? So instead, I only have to use 5 plus 3. So I only have to use 8 pins if I do it in this configuration where I connect all of the reds, all of the greens, and all of the blues together. So I can basically multiplex by using only 8 wires. And then, so that's how I handle all the multiplexing for the 5 LEDs in the front. And because I'm running it this way and I'm using a battery, I only have to use 3 resistors. Obviously, it would be better if you used a resistor for each one, but because I wanted this to be like pretty minimal at the same time, brightness wasn't really important. I'm actually kind of overdriving it, but that's because I'm not using a boost converter or anything. I'm just using the power straight off the battery, which can be anywhere between 4.2 to 2.7 volts once the protection circuit kicks in. So that's why I needed a pretty low resistance, just in case, like for the 2.7, but then it would still be good enough that the LEDs don't explode when it's at 4.2 volts. The only modification that I had to do to this Arduino Pro Mini was remove the voltage regulator, the 3.3 volt regulator. So you need to use an 8 megahertz 3.3 volt, or just 8 megahertz. It's automatically known that it will use 3.3 volts, but you could also use clock division as long as you're using 3 megahertz or not 3 megahertz. I'm sorry, 8 megahertz as your operating frequency, because the battery or the Arduino can't run well if it's like a 16 megahertz Arduino. It won't work below like 3.5 volts. Like, at least it won't work very stable. It has to be like 4.5 volts to be stable. So we just use the 8 megahertz one, and we have to remove the regulator. We don't actually have to, but I removed it because it's not going to be used in here. And you also have to remove either the LED or the resistor for the power. So, because that's just going to piss away like between 5 and 20 milliamps, so we don't need that. Or else, our battery is not going to last very long, especially since the lithium polymer battery that I use is only 400 milliamps. It's not going to last even 2 days if that little LED is plugged in, so I took that out. Now the battery charger is a TP4056 based charger. And yeah. So you see those LEDs? Okay, for the LEDs, I only use these because that's just what I had on hand. But yeah, use whatever you want. So as for the NTC thermistors, I use this style. So this one right here, this is a 10K NTC. You can usually find these inside of lithium-ion batteries from like laptops or really anywhere. They're pretty common. These are also pretty common in laptops and stuff. I would recommend that you use this or this, probably this, because the wires are insulated and you can just coat it with silicon and it won't care. It won't even notice. So the lithium polymer battery that I used was a flat type like this. It was only 400 milliamps, so ignore this 2000. But you can see, it's important that you have a protection circuit built into the battery, or if it's not built in, that you have one included. Because if your battery dips below like 2.7 volts, it's gonna be toast, or it won't last very long. And you also want to make sure that you protect it if it goes over 4.2 volts. So that's the purpose of this little PCB. And then the TP4056, I just use one of these generic boards that you can get off eBay. I bought like 15 of them for like a few bucks. There's a 1.2K resistor here, and you need to take that out and replace it with 5K. So I think it's 053 is the surface mount value. So 053 meaning 5, and then the 3 meaning K. So, or 103 is, yeah, K. 10K. Oh, yeah, 5K. That's what I meant. Or you can just use two 10K resistors, put them in parallel, or just use a regular 5K resistor or 4.7K. As long as it's not 1.2, because that gives a charging current of like 1 amp, and you at 400 milliamps, you really want to charge it at somewhere like maybe 50 milliamps or less. But yeah, and then this is a picture of an Arduino that uses 3.3 volts. We attach the battery straight onto VCC. Now for the actual circuit, get your pencils, everyone. It's time to start copying. I'll have screenshots of all of this stuff in the description. So you can see here how I multiplex it all on the same lines. Now I don't quite follow like D0 through D9. Like why did I put like it's pin 9 goes to the red strip, but then all of a sudden like 8 and 7 go into V plus, and then 7 and 6 go into green and blue. It's because 5, 6, and 9 are PWM pins, and the fewer PWM pins are. I did it because one, it was physically closer, so the lesser wires that have to jump over everything, the more compact you can make it, obviously. And I wanted them to at least be able to fade. So as long as I can PWM the colors themselves and then control the actual LEDs, like which one will turn on. Obviously the signals are inverted for PWM now because of the way that it's going for a negative. So instead of 255 being full brightness, 0 is full brightness and 255 is 0 brightness. So that's just the way that I do the multiplexing. It's a little bit backwards. It's not the best, but it works and it's simple. I do not power the soil sensors and the temperature and photoresistors all the time because the waste battery. It's not going to be much, but it's still wasting power. So I actually, every time I do an analog read, so if I want to do an analog read of the soil sensor, I actually have to turn on pin D11, and it sends voltage through the 10K or 100K resistor into the soil, and then I read the voltage difference between the soil and ground to A1. And then if I ever want to read the photoresistor and the NTC, since I can do those at the same time, or not really at the same time, but like it doesn't matter. I can constantly probe them if I want. I just put those on a different pin so I can turn those on whenever. like I could have isolated them from each other, but really like it's not much power, and I usually sense both at the same time anyway, so there's really no point. Right here is the actual TP4056 charger, and the Arduino understands if the battery is charging by probing the negative of the red LED through a voltage difference created by the actual USB input and the LED. Since it's a red LED and it has a supposed 2.2 volt drop, so 5 volts minus 2.2, that's like 3.3 or 3.8 volts ish, somewhere there. It's basically logic level high between this resistor and the LED. If I were to probe the actual charge, it would be negative. So I would actually have to do an invert on, or a not digital read high, basically, if I wanted to probe this part. But since this part is easier to actually solder a wire to, since I have 2 points of connection, it's just easier. So I picked that. And reading high as enabled is it makes more sense. I do not use the temperature connection on the TP4056 just because my battery didn't have one. On the actual UART connector, so I didn't include a USB UART. Like I could have actually soldered onto the USB wires on the charger and had it go through a RS-232 converter and then to the UART pins, but like this thing is meant to be standalone. Like you shouldn't need to use the debugger that I've built into it. It's really just for like making the custom profile curves of each different plant that you use, but really it shouldn't even bother being connected. So when you program it, if you already have the battery installed, you do not connect your programmer to the VCC connection, or else you're going to fry your battery. You could, as long as your battery is safe, like you could do it, but you might start melting your LEDs and stuff. But as long as your circuit is powered up or it's charging, you should be fine on voltage. So you only have to connect ground, RX, TX, and the DTR, the automated reset line. And those are all just on the bottom, as you can see here. So I actually just have a right angle header that goes over it. Then I just attach my female headers and I ignore this pin, which is the V+. Your Arduino may be different. So my Arduino actually doesn't look like this. My A6 and A7 were actually over here. So that's why in the code, like I don't use, like I use A1, A2, and then all of a sudden A6. That's just because it's physically closer to the sensor. So yeah, I mean you can always change the values. What the hell was I talking about? I'm like totally losing track, and this video is probably like a million minutes now. Okay, so here's the code. I have this really long bullshit up here, and so let's just go over it a bit. So you can define your the different care profiles. Can I zoom in on this? Nope, guess not. So you can define your care profiles. I have it right now set to fat succulent. Now I made all of these profile values myself, just Googling different things like temperature max and temperature min, soil max and soil min, which is the actual like wetness values, I guess, or resistance values that are read on the ADC. I haven't created some kind of scaling for a 0 to 100%, which I should do. Humidity, I plan on doing a 0 to 100% scaling, and this can be connected using one of those temperature or temp and humidity sensors that I think they use either one-wire communication or I2C. That's why I left ADC pins 4 and 5 free, so that I can use I2C in the future for expandability, or if I wanted to like extend I/O, so that I can do like things like control an external light or soil heaters, anything like that. And I actually also have a light hour, so the amount of hours that is the minimum for the plant, so that way I can sense like, oh, is the plant getting enough light, kind of thing. I also need to set like a lumen amount, so that would actually do the counter for the light hours, but as you can see right here, currently not in use. So I've set a couple different profiles. So this is bat succulent. Here's dry succulent, desert, tropical, and aquatic. Obviously, aquatic is like ridiculous. It's basically underwater, but that's so that the this thing is actually expandable. So like if I didn't make it inside of some wooden pot and I wanted it in an aquarium, obviously I wouldn't need the soil wetness thing, but that's for the sake of the code. Use a couple libraries, so the low power library by Rocket Screen and the math for the logarithmic stuff for the temperature sensor. Do all my hardware stuff here, so you can change these values depending on how you set up your own thing. I was planning on reading the battery voltage, but you need a reference to compare it to, and I was originally planning on using a 1.8 volt reference and then using a voltage divider, but that was a little bit overkill, and I'd rather just like, oh, is it flashing anymore? Oh, it's not flashing. I think the battery's dead. By my calculations, using the Rocket Screen library and like measuring off the current, using a really low current sensor, like I'm estimating 4 weeks at best, or maybe even at worst, depending on how bad you are at taking care of it. Because the worse that you take care of it, the more the LEDs will be flashing and stuff. If it's all good, then during the daytime, well, I mean, you can read this code and you can try it out for yourself. But during the daytime, if the sensor reads that there's enough light and all good, then it only blinks the center LED green for like half a second. It just fades it out really quick. But at nighttime, if it's all good, then it blinks nothing. But during the daytime, if there's something that needs to happen, it'll do this little wave animation, but in full brightness. Because it's daytime and you want to be able to see the LEDs. But at nighttime, if it needs some care, then it will run at like very dim settings. But it'll pulse every minute. So it does a check every minute, and it does a soil check every 15 minutes. I've extended that to every 30 minutes because from my tests in the last day and a half, 30 minutes is okay. I would even say I would even increase it to an hour. So yeah, right here is the slow counter and fast counter. The slow counter counts every time it goes to sleep, so it adds 29 minutes to the counter, or 29 counts. Or it requires 29 counts to get the soil measurement. And then for the fast counter, say it's in debug mode or in party mode, then it waits until it gets 100 or 1,920 cycles because it's not going to sleep. The debug stuff, it just prints out the values of the sensors. This one just resets the LEDs to like a thing before it starts doing anything. And then this is where it starts making judgment calls on like, if this is the temp sensor and the soil sensor area of the code are to judge or compare the actual sensor data to the care profiles. And then if you're in demo mode, it has a few little extra animations on the LEDs. Yeah, demo mode again. Demo mode is basically just a fade, and it looks nice, so it's like if you have a party or whatever and you just kind of want to show it off, you can hit the reset button and then cover the light sensor, and it will go into demo mode or debug mode all on its own, so you don't have to reflash the code or anything. That is all done in the setup. So like, yeah, it would do all the hardware setup stuff, and then if you cover up the sensor, so like if light M is greater than 900, then it starts doing the check if you want to enable something. That's just like a neat way to like enable a debugger, enable like a certain feature that isn't normally there, especially if you don't want to reflash the code constantly. Especially also since we don't have a USB programmer plugged in all the time. Here are some of my methods. If you were to actually read through all of this, which I do recommend that you do because I want changes done to this code. It's really rough, and it's just stuff I just made up like on the spot. I could have done better things. I could have had better animations using arrays and stuff like that. But it's just I have limited time, and I just wanted to make something that worked, and I knew how it worked. But yeah, that's basically it. Thanks for watching. This video is going to be pretty long. I'm not editing any of it. Yeah.